evening and welcome to another GWPF talk. Gives me great pleasure to introduce Professor Nir Shaviv from the Hebrew University in Jerusalem. You, I'm sure, know of him and his research. He is a physics professor at the Hebrew University, and he's the chairman actually of the physics department there, and has been researching the influence of solar activity on cosmic rays and climate change for more than 15 years. We are in the process of moving into perhaps the biggest scientific experiment of all time, which is we're approaching a solar minimum, which we can observe. We can see how solar activity is declining. And we now have two competing theories that have made predictions as to what the impact of the solar minimum, never mind a grand solar minimum, if it were to happen, will have on the climate. We have the conventional IPCC type consensus theory, which suggests that it will have a negligible influence on the global climate, and that in the next 20 years we will see a warming of somewhere between 0.4 and 0.6 degrees. So a decadal warming of somewhere between 0.2, 0.3, some people think 0.4 per decade. And we have the alternative theory that suggests that solar activity or inactivity will actually have a dampening effect on the global climate, which would mean that in the next 20 years the warming trend will either be much smaller or even return almost to pause conditions where we see hardly any warming. So we have now really a big test in front of us. And in many respects, it reminds me of another famous test in the history of science when Arthur Eddington went out to this famous 1919 solar eclipse and tried to test whether Albert Einstein's general theory of relativity could be observed, the bending of solar light as it moves along big objects. So I think Nir will explain the theory that I just mentioned as an alternative that can be tested, will be tested, and I'm afraid you will have to wait roughly 10 to 20 years for the results to come in, but I think we are really facing a very exciting period of time where competing theories are competing and will be tested. Nir.
Hi, it's a pleasure being here. London is always nice to visit, except for the, it doesn't matter when you visit, the weather is not something to write home about. But the city is always fun. I'm going to talk about global warming. Just a question before I begin. How many of you have heard my colleague Henrik Svensmark, who was here not too long ago? Only a few. Svensmark, yes. Oh, that Danish guy, yes. So quite a few. Okay, so I wanted to know how much should I overlap with what he said or not. Okay, so what I want to talk about is, as Benny introduced, talk about the fact that the sun has a large effect on climate and understand how, well, first of all, to see the evidence that the sun has a large effect on climate, understand where this link is actually coming from, and then understand what is the implication of this link to the understanding of 20th century climate change and 21st century climate change as well, namely to predict what will happen in the future, which, as Benny said in the introduction, is going to be quite benign. So I want to talk about the solar climate link, and then I'm going to demonstrate that the link is through, as Henrik demonstrated as well, through the fact that solar activity modulates the amount of cosmic rays reaching the Earth, and with that, the amount of ionization that we have in the atmosphere. This is well known. We also know from more recent empirical evidence is that this ionization plays a role in the formation of cloud condensation nuclei, and therefore the characteristics of the clouds, how white they are, how much of the sunlight will reflect back to space, and therefore temperature on Earth. So I'll show you the empirical evidence, and I'll tell you what the physical mechanisms are, because actually there are several, and then understand the implications. Okay, so let's begin with the solar climate link. To begin with, the sun is a variable. It means that various things that the sun output, whether it's the total irradiance or other non-thermal components of the sun, change together with the solar activity. To begin with, we have something like the 11-year solar cycle. Every 11 years or so, the magnetic field of the sun switches polarity. But overlaid on that, there are long secular variations which change the overall activity of the sun. For example, in the latter half of the 17th century, the sun was particularly inactive, and in parallel to that, we had the Little Ice Age. We had frost fairs on the Thames every so often. You couldn't grow wines in the UK anymore. Okay, you could do that in the Middle Ages. So the only vines left are in street names. On the other hand, during the Middle Ages, it was quite warm. It was warm here. Vikings could encircle Greenland. They actually called it Greenland, but maybe it was a PR stunt. But still, there was no ice there in the northern shores of Greenland during summer. So you have these variations you have these long-term variations in solar activity, which, as I already hinted, correlate with climate variations on Earth. So the sun is variable. The first person to actually think that there might be some correlation between solar activity and climate on Earth is Sir William Herschel. He didn't have any good climate measurement, so he used the proxy, and that was the price of wheat in the London Wheat Exchange, under the assumption that the price of wheat is going to depend on how well whether the climate is warmer or not. And he claims in a somewhat opaque article, if you want to read it, that there is a correlation. Going forward 200 years, this guy, Jack Eddy, he showed us that if you try to reconstruct the climate in this case in Western Europe, for example, the severity of winters here in London and in Paris, you find that there's a correlation between climate here and the activity of the sun. For example, as I said, the latter 50 years of the 17th century, on one hand, solar activity was particularly low. For 50 years, there were almost no sunspots measured on on the sun. And in parallel, we had the Little Ice Age. And during the Middle Ages, the sun was active, and winters were warm here. Okay, this is probably one of the nicest correlation you can find between solar activity on one hand and climate on Earth. At the top, you have carbon-14 reconstructed from tree rings. Basically, what happened is carbon-14 is formed by high-energy particles coming from outside the solar system. They're called cosmic rays. They hit the atmosphere, and they break down the nitrogen and oxygen into lighter isotopes, including, for example, carbon-14. The carbon-14 oxidizes, and then the trees breathe this CO2, and you find this carbon-14 in the tree rings. So by measuring the amount of carbon-14 in the tree rings, you know how much or how many cosmic rays, what was the flux of cosmic rays reaching Earth. However, this flux is affected by the solar wind and therefore solar activity. When the sun is more active, you have a stronger solar wind, and less of these high energy particles can reach the Earth. So you get less of this carbon-14. So by measuring the amount of carbon-14 in the tree rings, you can reconstruct what the sun was doing. So here you have a proxy for solar activity. At the bottom, you have something else. This is oxygen 18 to oxygen 16 isotope ratios in stalagmites in a cave in Oman, in the southern peninsula. And water to this cave actually comes from the Indian Ocean. And this here is a proxy of the temperature of the Indian Ocean. And the reason is that water with oxygen 18 is heavier than water with oxygen 16. So the evaporation rate is different. But it varies with the temperature of the oceans, the ratio between the evaporation rates. So what you have here is a proxy of the temperature of the Indian Ocean on one hand, and a proxy of solar activity at the top. And you see a correlation, right? So it means one of two things. Either the sun has an effect on climate, or maybe Earth's climate has an effect on the sun. Okay, this is another example. You find here at the, let's see, in blue you have again the carbon-14, and in black you have what's called ice-rafted debris. You have coals from the ocean floor, and this is from the northern Atlantic. And what happens is that on colder years, you have more ice float further south, and when it melts, it leaves the ice-rafted debris further south. So you can know whether it was warmer or colder in the North Atlantic. And again, you see a very nice correlation between solar activity and, this time, climate of the northern Atlantic. So obviously, variations in solar activity affect the climate on Earth. Here you see something similar. In red, we have solar activity, and in black, you have the rate of change of the sea level in millimeters per year as obtained from using tide gauges. And basically, what you see is that when the sun is active, the oceans are rising. When the sun is inactive, the oceans are falling. On short timescales, most of the sea level change is because of thermal expansion. In fact, 80% of the signal over the 11-year solar cycle should come from thermal expansion and not from melting of glaciers. So basically what we see here is a calorimetric measurement of the forcing that the sun has on the climate. Basically, you can quantify in watts per square meter how much solar activity translates into changes in the energy balance. Why is it important? It's important because when you quantify it, you find that it's very large, and how large we'll see in a second. If you don't believe, if you think this correlation is a fluke, what you could do is use more recent satellite altimetry data, and if you remove the linear trend, the fact that the sea levels are rising because glaciers are melting, you find that if you build a model for the sea level here is plotted in blue. The purple is a model which includes only two things, the sun and El Niño Southern Oscillation. And you see that these two things explain almost all the sea level change on short timescales, again, with the linear trend removed. So the sun has a large effect on climate. It's there, you cannot ignore it, and with this correlation or with this correlation, you can actually quantify how large it is. So how large is it? What you see here is the peak-to-peak variation in watts per square meter as obtained with the satellite altimetry or with the tide gauges or with other measurements that I didn't show you due to lack of time, but if you ask me at the end, I can explain what they are. And for comparison, these are the changes that you expect in the solar irradiance. Okay, so just the changes in the solar luminosity, the amount of radiation we get directly from the sun, should correspond to this amount in watts per square meter over the solar cycle. The IPCC, incidentally, is saying that it's even less than this, because from one report to the other, they try to diminish the effect that the sun has, even more so, which is quite embarrassing. But in any case, for them, not for me. In any case, the interesting point to take from here is the fact that the change in the solar forcing that you get as you measure with the, say, the ocean, the colorimetric measurement of the oceans, and the solar irradiance itself, this discrepancy implies that there must be a mechanism amplifying solar activity. There must be something which makes our climate more sensitive to the climate, to changes in the solar irradiance. A hint for that you can actually get from here. There are cloud variations over the solar cycles. And if you translate those cloud variations into a change in the energy budget because of the change, the albedo, you find that it gives you consistently the same change in the forcing. So what it tells you is that the sun has a large effect on the climate, and it is much larger than changes in the irradiance, and you must take it into account. This is the changes in the radiative forcing from the 5th assessment report of the IPCC. These are, of course, the well-mixed greenhouse gases and other things. These are the indirect aerosol effects. This is another embarrassing point to the IPCC, the fact that they don't know how large we actually contributed some cooling to the climate because the aerosols affect the clouds. But this is what they tell us is the change in the solar forcing over the 20th century, or from the industrial revolution. This is very small. If you consider the fact that solar activity increased over the 20th century, and you translate that into a change in the radiative forcing, you would get this value. Okay? So this is the elephant in the room that the IPCC is totally ignoring. They're ignoring the graph I showed you before, even though it's clear as daylight that the sun has a large effect on climate. And over the 20th century, this is the radiative forcing that they should have taken into account. Where is it in all the IPCC reports? It isn't. They're totally ignoring it. Okay, and this changes the whole story. Okay, so we know the sun has a large effect on climate. We know that it should be a mechanism other than the solar irradiance. In principle, you don't have to listen to this part anymore because you know you have to take the sun into account. But as a scientist, I'm interested to know what is this physical link all about? Where is this physical link arising from? So this is what I'm going to tell you about now. The physical link is as follows. I told you about the cosmic rays, these high energy particles which affect the climate on Earth. These cosmic rays actually come from massive stars, stars which are more massive than about 10 times the solar mass. They die in large explosions, and these large explosions, those stars shed the outer layers at high velocities. They collide with the interstellar medium and accelerate particles to high energies. Then these particles diffuse in the Milky Way, they reach the solar system, and when they reach Earth's atmosphere, they not only cause spallation and form, for example, carbon-14, they're actually the dominant source of ions. I mean, here it might be radon coming from the ground, but if you go out, almost all the ionization in the atmosphere is due to these high energy particles coming from supernovae that exploded typically 10 million years ago. These ions play a role in the nucleation of small aerosols, typically a few nanometers in size, and we now know they also play a role in the growth into large 50 nanometer sized particles, which are called cloud condensation nuclei, because if they're larger than typically 50 nanometers, when we reach conditions of nearly 100% humidity and want to form clouds, if we have these particles around, the water vapor can condense on them and form clouds. So, I mean, we always have cloud condensation nuclei, but the question is whether we have more of them or less of them. When we have more of them, then we get droplets with, which are typically smaller, but they're more numerous, and they have a larger surface to volume ratio, which means that they're going to reflect more of the sunlight. So basically what happens is the following. When the sun is more active and it has a stronger solar wind, less of these high energy particles can reach the solar system, so you ionize less of the atmosphere. If you ionize less of the atmosphere, you nucleate less small condensation nuclei, and less of these condensation nuclei can survive the growth to become large cloud condensation nuclei. So you have less cloud condensation nuclei. So you get clouds which are less white. And these clouds which are less white reflect less of the sunlight, which means that more of the sunlight can penetrate Earth's atmosphere and reach the surface and warm us. Okay, so this is the link. And we have evidence for each and every part of this of the story I told you just now. Some of it is empirical evidence, some is evidence that we can go into the lab and measure the mechanisms themselves. But we have now evidence for everything I just told you. Okay. Okay. Okay, to begin with, this, what you see here is a correlation between the cosmic ray flux reaching the Earth in red and the amount of low altitude cloud cover. And obviously you see a very nice correlation, which suggests that the two things are related. This change in low altitude clouds can be used to estimate what is the change in the energy budget due to the fact that clouds are white and reflect the sun. And that can, when you translate that, you get the same 1 watt per square meter, which you see entering the oceans every solar cycle. So this amplitude is consistent with what you actually measure with the oceans. Here is another example. Sometimes you have a gust in the solar winds called Forbush decreases. And this gust in the solar wind decrease the flux of cosmic rays that reaches the Earth. And as a response to these decreases in cosmic ray flux, you see that the amount of aerosols on Earth decreases, the amount of cloud condensation nuclei, as well as various different cloud parameters which are measured by different satellite experiments. So you see that when the sun has a gust in the solar wind, it reduces the cosmic ray flux, and as a response, we get less aerosols and clouds which are less white on Earth. Okay, so you actually see the mechanism operating. You can also go to very long timescales, which is actually the way I entered this field so many years ago. You can reconstruct the cosmic ray flux on Earth using iron meteorites. And when you do that, you find that the cosmic ray flux on Earth varied roughly periodically. There are actually 7 oscillations in the cosmic ray flux over the past billion years, which are naturally explained by the fact that every so often, every about 145 million years, we pass through a spiral arm of the Milky Way. And then you can also reconstruct the temperature on Earth. Again, this is oxygen reconstruction based on oxygen 18 to oxygen 16 isotopes from fossils that you find, in this case, tropical oceans, over the past 500 million years, because that's when you had multicellular fossils. And you find that there is a very nice correlation between the cosmic ray flux and the geological reconstruction of the temperature. So it varies. Incidentally, you can also, in addition to the fact that we pass through spiral arms of the galaxy, we're also oscillating perpendicular to the galactic plane with a period of about 64 million years, which means that every about 32 million years, we cross the galactic plane. And if you remove the 145 million year oscillation, reconstruct the temperature over the past 500 million years, you find that you can naturally explain it with the vertical oscillation of the solar system. So over geological timescales, this link actually explains most of the temperature change on Earth. I can talk about it a little bit more if you ask me during the questions. The interesting thing is that not only do you see the vertical oscillation, you see that there's a secondary oscillation which is due to the fact that as we rotate around the galaxy, we're sometimes closer to the galactic center, sometimes we're further out, and when we're closer to the galactic center, the density at the galactic plane is larger, so we're oscillating faster. You see that with the geological data. So the theory predicts interesting things which you can then go and find actually operating. Okay, so going back to the link, I can show you that you can go into the lab and see that when you increase the ionization, you increase the condensation nuclei. This is an experiment that Henrik and his group in Denmark carried out more than a decade ago. This is from 2000 and published in 2007. You see that when you increase the ionization, you increase the number density of condensation nuclei. A few years later, it was redone and corroborated at CERN, at the cloud experiment at CERN. You see that when you increase the ionization in the chamber, you increase the nucleation rate of aerosols. So if you increase the ionization, you get more condensation nuclei. You can also see that if you increase the ionization, you increase the survival of small aerosols to become large ones. Here you see two experiments. In this experiment, you see the relative change in the aerosols as a function of size when you inject small aerosols by hand. Here what happens is that instead of injecting the aerosols by hand, you increase the ionization. So if you increase the ionization, you increase the nucleation of small aerosols. But in this case, you increase the nucleation of small aerosols, but the relative increase as a function of size decreases, and that's because many of the small aerosols, or the additional aerosols that you nucleated, stick to larger aerosols as they grow, so they don't survive to become large. On the other hand, if you form the ions, if you increase the ionization in the chamber, not only do you nucleate more, you allow more of the small aerosols to survive to become large cloud condensation nuclei. So there's an additional mechanism operating. If you increase the number of cloud condensation nuclei, you can see, if you just Google ship tracks, you will see these kind of pictures. This is the marine layer opposite of California and Oregon. And you see that wherever ships pass and left all the particles, all the exhaust particles, because it's international water, so they burn the dirtiest and cheapest fuel possible. So that serves as a cloud condensation nuclei. Here you can see the cloud of aerosol, no, it's not cloud, the aerosol, sorry, not the aerosols, the exhaust particles left on a cruise ship. I was on a cruise ship next to Greece, and the most interesting thing to do is to take a picture of the exhaust particles. So you pass, you leave those exhaust particles, and then over them, if you reach 100% humidity, you find that the clouds formed are much whiter. So you see that if you increase the cloud condensation nuclei, you form clouds which are much whiter. Okay, so this is the experiment in Copenhagen, which I joined a few years ago. This is what happens when a theoretician goes into a lab. So in the chamber, we can measure various processes taking place. We have a mass spectrometer to measure the gases and the ions clusters. We have a particle, what is it? We have a particle counter, it's this thing, which can measure the sizes of the spectrum of particles we have in the chamber as a function of size and as a function of time. We have a UV light at the back of the chamber, which can start a photolysis reaction. Basically, you break down water, and then it oxidizes SO2, and you get sulfuric acid, which is the building block of the aerosols. So, this is actually something I built myself as a theoretician. I built something where you can control the amount of gamma rays that you get from the gamma ray sources. So you can automatically increase or decrease the ionization in the chamber. I cast the LEDs in Israel because it was a third of the price of doing it in Denmark. So I flew with 23 kilograms of lead in a small trolley, and it looked very strange. But I passed it. Anyway, because we can do it automatically, one of the two mechanisms that operates and are responsible for the survival sorry, of the aerosols, one of these mechanisms is hard to see in the lab because it's relatively small under the conditions we can simulate in the lab. And we have to repeat the experiment many times in order to get a high signal-to-noise ratio. So this is actually a mechanism that would be very hard to detect in the experiment at CERN because they cannot do this kind of long runs. Okay, so what are the two experiments? Okay, so we can we have gamma ray sources and we increase ionization in the chamber and actually measure the mechanisms themselves that are operating. I'll skip over the mechanisms themselves. If someone is particularly curious what's the physics behind it, I'll leave it to the questions. Okay, so what are the implications? We know the sun has a large effect on climate. Today, because of our of the empirical results and the experiments, we have evidence for the actual mechanisms taking place, and we understand exactly what's going on. What are then the implications of this link, the fact that the sun has a large effect on climate, on our understanding of the 20th century and 21st century climate change? We have to realize that the IPCC, if you open the IPCC reports, there are no direct pieces of evidence which contradict anything that I told you or anything that I will tell you. The reason that the IPCC reports actually quote unquote prove that humans are responsible for most of the warming and therefore climate is relatively sensitive to changes in the radiative forcing and therefore climate change over the 21st century is going to be large. The reason that they can implicate us humans are the following. From all the arguments you find in the report, basically it boils down to those two arguments. First, the warming is unprecedented, and if it's unprecedented, it must be humans. The second argument is that if you try to simulate what has happened over the 20th century and you exclude the effect of humans, you cannot explain what has gone on, and therefore humans must have had a large effect on climate. So why are these arguments wrong? Okay, so first of all, we all heard of the hockey stick, right? Until in the first and second assessment reports of the IPCC, we could all find the discussion about the medieval warm period and the Little Ice Age and so forth. And then suddenly we woke one day in 2001, and like George Orwell's 1984, you wake and history has changed. There was no medieval warm period, there was no Little Ice Age, just the temperature which almost didn't change. And then suddenly, over the 20th century, it started to skyrocket. And we all know if you Google a climate gate, you'll realize that what has happened is that in 1961, the tree-ring data showed a temperature decrease, so they cut it away, and they stitched thermometer data, obviously mixing two very heterogeneous data sets together and getting garbage, or as they say in this land, yes, rubbish. Okay, the second argument is the following. These are the radiative forcings as a function of time over the 20th century. This is the well-mixed greenhouse gases. These are the uncertain aerosols. These, for example, are volcanic eruptions. You put these radiative forcings into global circulation models. You let the CPU crank the data, the model, and you get many realizations. These are the mastered realizations. You can compare that to the measured temperature over the 20th century, and lo and behold, you can explain the 20th century. Actually, you cannot, because there are large discrepancies. Every time there was a large volcanic eruption, the models give you that the temperature should have decreased by much more than what the actual temperature decrease was. Typically, the models give that the reduction following Pinatubo or Krakatau should have been something of order 0.3 to 0.5 degrees. But in reality, it's only 0.1 degree. Which means that the models are actually not doing that well. But still, they claim that, ta-da, you can explain the 20th century if you include anthropogenic activity. On the other hand, if you exclude anthropogenic activity, and you try to do the same model integration, you find these cyan or bluish colored reconstructions with an average in the blue, and you see you cannot explain the temperature increase over the 20th century without taking the human activity into account, which means that humans must have had a large effect on climate. But this assumes implicitly that we know that there is something, that there isn't anything else that we're missing. But as I demonstrated, there is something we're missing, and that's the effect that the sun has on the climate. Okay, so these two arguments are simply wrong. And you don't find any other arguments, pseudo-scientific arguments, that with which you can incriminate humans or human activity on climate change. Nothing, okay? So what does that mean? If you try to explain 20th century warming with just the anthropogenic forcing, you need a high climate sensitivity in order to explain what has happened over the 20th century. On the other hand, what that means is that if you have a high climate sensitivity, a given emission scenario, for example, one where you will double the amount of CO2, will give you a relatively large temperature increase over the 21st century. On the other hand, if you have a much larger radiative forcing, because the sun has a large effect on climate, it means that the total radiative forcing is larger, and therefore you need a low climate sensitivity, which in order to explain the 20th century. This low climate sensitivity is something that actually you can get empirically if, for example, you try to look at the correlation between the CO2 over geological timescales and the temperature, something I didn't show you, and you can ask me about it later, or the fact that the response to volcanoes is small, or half a dozen other timescales where you see empirically that Earth's climate sensitivity is on the low side. So the empirical data actually tells you it's on the low side, and this is what you need to explain 20th century climate change if there is an additional forcing, which there is, namely the sun. Now, if climate is relatively insensitive, then the temperature increase over the 21st century for the same emission scenario should now be much more benign. Okay, how much? You can build a model which includes the diffusion of heat into the oceans and the fact that the sun has a direct effect and an indirect effect, and leave things as free parameters and try to explain what has happened over the 21st century. And this is what you get. If you try to explain 20th century climate change while allowing the sun to have a large effect on climate, you find that you can explain the temperature increase. So one of the graphs here is the model, and the other one is the actual temperature reconstruction. And I don't know which one is which because they're actually very similar. On the other hand, you can compare it to what the IPCC tells us the model can do. The reason that this model can do a much better, can fit the data much better than the IPCC models is because this model allows for the sun to have a large effect on climate, and the solar activity increased until the 1940s and decreased until the 1970s and so forth, and that explains much of the variation that you see here in the temperature. So by allowing the sun to have a large effect on climate, we can actually explain 20th century climate change much better. Anyway, so what we find, if you allow the sun to have a large effect on climate and you look at empirical evidence, including, for example, this one, is that if you double the amount of CO2, the temperature on Earth is going to increase by between 1 and 1.5 degrees centigrade. On the other hand, if you open all the IPCC reports, except the penultimate one, all the IPCC reports tell us that if you double the amount of CO2, the temperature will increase anywhere between 1.5 to 4.5 degrees. And the 4.5 degrees are, this upper range implies that climate change is going to be catastrophic. But it's not. All the empirical evidence suggests otherwise. Okay, so you can use these models where you fit the 20th century and integrate forward in time, allowing for realizations for what the sun is going to do, what volcanic activity is going to be, and so forth. And these are many realizations for what the temperature increase over a vanilla-flavored emission scenario would be if you double the amount of, roughly if you double the amount of CO2. This is what the temperature increase is going to be compared to the IPCC range. Okay, so in Copenhagen and in Paris, the IPCC convened, and they said we want to make sure the temperature increase is going to be less than 2 degrees. It is going to be less than 2 degrees. Okay? Plus, I don't think we're going to double the amount of CO2 for other reasons. Like, we're not going to burn fossil fuels in 20 or 30 years. We're not going to do that because other things are going to be cheaper, but that's besides the point. Okay, so let me summarize. There is evidence, as clear as daylight, that the sun has a large effect on climate, and it goes hand in hand with evidence of low climate sensitivity. It implies that much of the warming over the 20th century, typically somewhere between half to 2/3, should be attributed to the sun. This low climate sensitivity implies that 21st century temperature increase is going to be very modest. There are no arguments that actually prove or that can be used to rule out this, this picture I presented. The evidence I showed you basically implies that the arguments that the IPCC brings is invalid. The arguments are invalid. Today, we also not only have the empirical evidence showing that the sun has a large effect on climate, we can actually go to the lab and do experiments and measure the mechanisms working. So the case closed, basically. And that's it.